Hello, everyone, and thank you for attending this session virtually. So my name is Laura Dalton. I am a PhD student at North Carolina State University, working under my advisor, Dr. Mohammad Pour-Ghaz. And today I will be talking about the effect of gas solubility on water sorption rate in cement-based materials using X-ray CT. So a little bit on the research motivation here. I have an image of a well casing. And so throughout the United States, there are over 1.7 million of these underground wells, and they're constructed with steel and cement-based materials. And after some of these are depleted of their resources, we use them for long-term storage of carbon dioxide. And then in some cases, we come in and seal them with concrete. And really what I'm interested in is what is the service life and long-term durability of these systems. So, and improving on the fundamental understanding of mass transport in these systems. So, the research question that we came up with from this, so here I show a sorption plot. On the x-axis, we have the square root of time, and on the y-axis, we have the degree of saturation, which is the void space that becomes filled with water over time in your cement-based material. So in cement-based material, this is actually a bilinear plot where we have an initial sorptivity slope and a secondary sorptivity slope. So what does that mean? So this is a two-part process, and initially the water is absorbed by, so you have your dry cement paste, and initially water, if you put that cement paste in contact with water, the capillary forces dominate, and that will fill the capillary and gel pores, and this is your initial sorption. And once that process is ended, you then go into a secondary portion, which is the slower movement of water into larger air voids. And this is the secondary sorption process. And this mechanism is dominated by the dissolution and diffusion of gas within the air void. And this is a much slower process because the diffusion and dissolution of air and water is much slower than capillary suction of water into the cement-based material. And this will happen until you reach a critical degree of saturation, which is where things go wrong when it comes to durability in these systems. So in our above ground systems, all the air voids are filled with air. That's just what's in our atmosphere. But when it comes to these below ground systems, a well breach, or who knows what could go wrong in the future, the idea of what would happen if these air voids are filled with a gas other than air is kind of what I'm interested in. So the solubility limit of air is quite small, and that's what's actually used to enhance freeze thaw in our above ground infrastructure. However, CO2 and methane have slightly higher solubility limits in water compared to air or nitrogen. In fact, CO2 is nearly 50 times higher than that of nitrogen. And so in the secondary sorption process, that's really what we're interested in, is what would happen if we replaced the air filling these voids with a different gas phase, and what effect would that have? I also mentioned that diffusion also plays a role. However, the diffusion coefficient of each of these gas phases is very similar. So really the research question is, does the solubility of a gas phase influence the ingress of water in a cement-based material? And so an overview of our methods. So how can we measure these differences if they do exist? So we created an air entrained mortar, just a single one to keep it simple. And then we purged the different mortars with pure gas phases, so CO2, methane, and then another sample with nitrogen. And we wanted to deal with single gas compositions just to keep it simple for this first round of experiments. So then we brought water in contact with each of our mortar specimens, and then from there used X-ray microcomputed tomography to monitor the gas and water interaction in the air entrained voids that were easily resolved using CT scanning. And we observed this for 24 hours using CT scans. So here are the mixture proportions for the mortar that was used. Here is our sample. It's a 1/4 inch sample, very small, and it was cut using a diamond wet saw to make sure that we didn't have any microcracking, because that could lead to preferential flow paths, which we wanted to make sure did not happen. And then I ran these experiments at the National Energy Technology Laboratory in Morgantown, West Virginia. And so here's an overview of the system there, and don't get too distracted by this image. This is just to show. So we have some pumps on the outside of the micro CT system, and this is how we can inject these different gases then into this micro CT system where our sample will be housed for CT scanning. So, and I'm going to talk about this more in subsequent slides. So now we're looking inside the micro CT system, and this is our vessel that we put our sample in. And so I took an X-ray radiograph of that. So it's just like if you had an X-ray scan of your arm to look at a bone. So we're looking inside this vessel to see how our sample is set up for the testing. So here's the mortar sample. We have our aluminum vessel, which is seen in the image. We have a sleeve that connects the inlet and outlet injection ports that are above and below the mortar sample. And then we have a Teflon spacer, which I will talk about more. It's really only important when we discuss the water injection. And then, yes, the injection port for the gas. So we then come in and we inject a gas phase. So we want to remove all the air from the system. So we injected CO2 into the system overnight. So we basically just did a pressure gradient across the injection pump to the receiving pump. And then the next morning, I came in and manually injected water using clear tubing until I could no longer visually observe the injection. And then I used X-ray radiographs and that Teflon spacer I mentioned earlier to actually monitor the water filling just below the sample, because we wanted to make sure that we brought the water in contact with the sample, but didn't inject water into the sample, because that would not be the capillary suction process. That would be a pressure gradient, which is not what we wanted. So once we almost filled that system, we then put a vacuum pump just to bring the water very slowly into contact with the sample. Once there was contact, we cut it off and let the capillary action take over, and we started CT scanning. So here you just see one of our samples in the 3D rotating image, and we did 30-minute scans for 24 hours. So that was a total of 48 scans. And a quick look at some of the X-ray CT images are shown here. So this is that first scan from 30 minutes, then 60 minutes, then 90 minutes, and so on. And as you can see in this entrained void close to the bottom of the sample, it's first filled with a gas, that's the dark phase. And then by 120 minutes, you can see that a lighter phase has moved into the void space. So this is the water that is being absorbed and dissolving into the air void that is filled with CO2 in this case. And then by 180 minutes, it's basically completely filled with water. So then I repeated this with a new mortar sample purged with methane, and then another third experiment with nitrogen. And then all experiment image processing was completed using ImageJ. So then here, what I'm showing is I've extracted the entrained void system out of each of my samples. So here on the left in red, we have the CO2 filled voids. In the middle, we have the methane filled voids. And then on the right in green, we have the nitrogen filled pore system. And the first observation from this is that within 30 minutes, in an hour, we saw water advancing into the entrained void system, which, if you remember, the solubility limit is much higher in the CO2 in water compared to that of methane or nitrogen in water. And even at 2 hours, we're still not seeing any advancement in the methane or the nitrogen sample relative to the CO2 filled voids. And then we eventually reach even 6 hours, and the CO2 filled voids have actually become completely saturated with water and still no change with methane or nitrogen. It's not until about 12 hours that we observed a change in the methane sample, and not until about 24 hours that we observed a change in the nitrogen, which, if you remember, also the solubility limits of methane and nitrogen are fairly similar. So we were a little perplexed by the fact that they didn't occur at more similar points in time, but this will be discussed in later slides. So the next thing I looked at was actually extracting a single void from along the height of each sample, just to get a more detailed understanding of what was happening in each of these samples. So here are the results for the CO2 filled void system. So here is a single void extracted from close to the bottom. So on the x-axis here, we have the square root of time, and on the y-axis, we have the height of the sample. So this is a single void and how it was changing with time towards the bottom of that sample. And then towards the middle of that sample, so slightly higher up, and then another one even higher along the sample than in the middle. So, and why I'm showing these in slightly different colors. So if you remember from the CT scan slices, a gas will show up as like a darker black color, whereas water shows up as a lighter color. And what we observed was that as the water became CO2 saturated, the attenuation was actually changing with time. And so that was an observation that was made, and that's just what's being shown here, that water compared to CO2 saturated water had a slightly different attenuation coefficient. And so I completed this with the methane filled voids as well. So one close to the bottom, which again didn't show any changes until about 12 hours. And then farther up on the sample, there really was no change observed, and even farther up, no change. And then for the nitrogen filled void, again, not much was seen over that 24-hour observation period. And that's going to be discussed more in later slides. And that was the same as you move up on the height of that sample. So we then completed thermogravimetric analysis, or TGA analysis. So according to literature, the thermal decomposition of calcium carbonate occurs somewhere between 550 to 700 degrees Celsius when using this method. I did 3 tests per specimen, one from approximately the top, middle, and bottom of the specimen, just to have randomized, but to be able to average and have a representative sample from each region of each of these samples. So then I averaged these, and they are reported on the right here. I also did a pre and post control sample. And the basic takeaway here was just that if there was more CO2 in the system, we observed more calcium carbonate formation. And so at the beginning of this, I talked about sorption plots. So I went ahead and was able to make those for each of the gas-filled systems. So we know that secondary sorptivity cannot occur until initial sorptivity has ended. So I use that to then, from the voids I extracted, those are my largest void systems. So that's what I'm interested in when it comes to the secondary sorption part of this plot. So when they were empty compared to as the water filled each of these, I was able to do a volume fraction to determine and make these points and plot the secondary sorption for each of these over that 24-hour window. And so there are 3 main takeaways from this plot. One, the CO2 filled voids became completely saturated almost nearly when the methane filled samples started to just fill with water. Second, the CO2 filled voids, there's kind of a non-linear behavior that's observed early on, and we'll talk about that in subsequent slides, and then it becomes more linear again. And then the third thing to note is that the methane filled sample did begin much faster than the nitrogen filled sample, the entire secondary sorption process, and we will discuss that more and why we believe that that happened in this case. So for the CO2 sorption process, we came up with a very simplified model. So we have a single gel pour and capillary pour connected to an entrained void. And so that's lined with calcium hydroxide. And so we purge these systems with the pure gas phase, in this case CO2. And then the initial sorption process took over, but the water that would have been injected into this system had dissolved air in it, because that's just what would naturally have dissolved in the air that we put into the system. And so what happens there is your CO2 starts to dissolve in the water, your calcium hydroxide also starts to dissolve in the water, and then they react and form calcium carbonate in the pore system. But you reach this point where the pressure in that internal entrained void is higher than the capillary suction. And so it then becomes a function of a concentration gradient, a diffusion concentration gradient, which we believe might be why that was nonlinear. There was nonlinear behavior in the previous sorption plot that was shown for the CO2. And only then did the secondary sorption process continue, and calcium carbonate continued to deposit in the pore space. Whereas in the methane sample, similar, but when you purge the system with methane, methane doesn't react with the calcium hydroxide to form calcium carbonate, similar to, or unlike CO2. So what happened here was a more natural transition where it went from being sorption process to a diffusion controlled process in the secondary sorption and the function of the dissolving into water. However, that the solubility limit is much lower, and so it was just a slower process relative to the CO2 filled sample. And lastly, the nitrogen filled system. So we purged with nitrogen. It's already filled with air, and air is nearly 80% nitrogen. So what we believe was happening here is that the water advancing into the system, because it was already pre-saturated, mostly to the point that the remaining nitrogen in filling those voids could not dissolve into the water, and that's why it was such a slower process relative to the methane filled sample, even though the solubility limit is very similar. So the basic takeaway there is, had we pre-saturated the water with CO2 in the CO2 filled system, it probably would have behaved more similar to the nitrogen filled sample. In the same case for methane, had it been pre-saturated, if the water had been pre-saturated with methane, the dissolution process could not occur at the same rate. And so the concluding remarks, methane filled with the methane filled sample filled with water nearly 5 times faster than the nitrogen filled voids. The CO2 filled voids filled with water nearly 200 times faster than the nitrogen filled voids. And the basic takeaway here is that the solubility of the gas phase is important in mass transport and affects the transport mechanisms that are involved in these processes. And this has implications for the long-term safety of underground wells. Also, this work was just accepted in Transport and Porous Media, so if you are interested in learning more about the details of this work, it should be published here in the next few weeks. And with that, I'd like to thank NATL and NC State for all the support on this work, and my advisor, Dr. Pour-Ghaz, for his guidance on this entire experiment, and also Karl Jarvis, who's from Nettle, who helped in making this experiment possible. So with that, I am happy to answer any questions, and thank you for your attention.
The first question is, how does underground well safety improve with this sorptivity information?
So the overlo the fundamental work of this was really just to understand mass transport and what would happen if, like, what role does the solubility of a gas phase have? So, so the rate of mass transport is mainly driven by external gas pressure in underground wells. However, at low pressures, the rate of transport of water and other fluids could be significantly affected by the gas solubility as a result of this study suggests. So that's really, there's ongoing work that's slightly more relevant to the lower portion of a well and those higher pressures and temperatures, if that's kind of what the question is. This
Okay.
isn't really related to the what I think is the bigger concern, which is higher pressure and temperatures in lower parts of a well, but this could still have impacts at those lower pressures.
What is your opinion on synergistic behavior with natural gas?
Synergistic behavior with natural gas. So, meaning what?
The way I'm interpreting this is if there's natural gas in the pores, perhaps?
Okay, that it honestly behaves fairly similarly to nitrogen because of this lower solubility limit. Um, so that's not really the big concern. The bigger concern is carbon dioxide in that it's both higher solubility limit and reactive diffusion is happening because of the calcium carbonate formation reaction that takes place. So that's the
Okay.
bigger concern, yes.
Okay. There's another question. What about the strength after filling voids with nitrogen and methane?
That's a good question. I mean, these are very small samples. We're talking an inch long by quarter-inch diameter. So to test the strength of those, I think that that would be a good study to complete in the future, or maybe upscaling it and doing it with more representative samples. That's a good point.